Hey everybody. So today I'm really struggling with chemistry, but I am slowly working on a plan. I know it's going to be a little bit crazy because we were doing modeling chemistry and now um, we're switching to kind of just a regular mm, chemistry class. And so it's going to take us a little bit to kind of catch some things up and tie up some ends so that we can kind of cover it a little more traditionally. So we're going to have to backtrack a little bit. So um, what we ended talking about in class was ionic compounds and the charges that different atoms form to form ionic compounds. And so um, one thing that we're stuck with is, why do atoms form these charges? We know that they lose electrons, but why do group 1 atoms only lose 1 electron? Why do they only form that 1 plus charge? Why do group 2 atoms only get a 2 plus charge by losing those 2 electrons? Why does group 15 gain 3 electrons and that's all they do? And then, why do the transition metals form multiple ions? How can they lose different set amounts of electrons but no other atoms can? And so we're going to have to study the atom a little bit more and try to discover more about it. And so if you remember, all we really know at this time is that we have a plum pudding model of the atom. So we have that really soft, squishy cookie dough, and then inside it are little chocolate chips. And so that positive cookie dough is like our positive charge in our atom, and those chocolate chips inside are the electrons within there. And so that's where we left off. And so we're going to do a little more studying, which is dealing with Ernest Rutherford. So I need to share my screen with you so that I can walk through some things with you. Okay. And get out of this. All right, so again, where we left off was J.J. Thomson's plum pudding model, and this is what we were looking at. Over here, there's a nice picture of plum pudding, because I don't think I ever showed you that, and a lot of us didn't know what it was, but there's our plum pudding. Again, all this outer material, kind of like a cookie or a cookie dough, is all positively charged, and there's these negative charges inside it. Again, this is J.J. Thomson's. And the next scientist that really studies the atom for us is Ernest Rutherford. Now, Ernest Rutherford is a student of J.J. Thomson's. And so what he's really trying to do is he wants to test the plum pudding model that his teacher, J.J. Thomson, proposed. And so Rutherford is going to set up a gold foil experiment. And so in this gold foil experiment, let me get this open here because this has a good little picture. What we have is we have an alpha particle emitter. Now, alpha particles are just helium atoms that only have their positive charge. And so all the electrons have been taken away from it. And so they have a 2 plus charge, and they're going to shoot these at a piece of gold foil. And so you can see the gold foil there inside of this ring. Now, this ring is a little detector. And so when alpha particles hit it, you're able to see where it hits. And so you can track the path of these alpha particles. Again, these are positively charged particles coming out of this box. Right, so based on what J.J. Thomson told us about the atom's supposed to be really soft and squishy, like plum pudding or like cookie dough. And so what Rutherford thinks is going to happen is that all our alpha particles should just go straight through this soft material. Yes, there could be a little bit of deflection because we're shooting positive particles at it. And so when they're coming in contact with some of this positive cookie dough, some of those particles could be deflected, but mostly we're going to see particles go straight through. And so if this was J.J. Thomson's plum pudding, and again, all these little blue dots in there are electrons, again, Rutherford thinks if we shoot alpha particles at them, these positive particles, our particles should go straight through. Again, there could be slight deflection due to positive charges, but nothing drastic. Right? So let's go watch Rutherford's experiment and we'll see what happens here. All right. I'll zoom ahead a little bit. All right, so again, we are going to shoot alpha particles out of this little emitter box. And so again, those are just positively charged particles, just helium atoms without their electrons. And we're shooting it out, and they are going to go and strike the gold foil. And so here it is. And when it happens, we're going to see that the particles do sometimes go straight through, but notice some of them are deflected at pretty wide angles. This one over here bounced clear back. These are emitted sideways. And so this is something that Rutherford did not expect. This means J.J. Thomson's model of the atom cannot be correct. So it's like every student's dream. He just proved his teacher wrong. And so now he's here to revise the model of the atom. And so he has to think, well, if the plum pudding model isn't correct, then what is the new model? What can be happening? And so he proposes a new idea. He proposes that we don't just have a soft, squishy, positive material with negative charges dispersed throughout it. We have to have this really dense positive charge within our particle. It can't be something that is scattered over throughout the particle. And so Rutherford proposes a nuclear model of the atom. And so what he does is he discovers the nucleus. And so early on, this is what Rutherford believed. He believes that we have an atom. So this whole white picture represents one atom. Within that atom, there's a nucleus at the center. That is where all the positive charge is. And then out here, this is mostly empty space, and the electrons are spread throughout that empty space. So again, his model of the atom, we have a dense center that contains all our positive charge. And then outside of that, we have big empty space in which electrons are moving around throughout. Over time, they discovered that there's more to the nucleus than that the nucleus actually contains protons and neutrons. And so the nuclear model, a little bit after the discovery of the nucleus, changed to contain protons and neutrons within the inside the nucleus. But still, outside of that was mostly empty space in which the electrons zoomed around and occupied that. But again, the atom is a majority of open space. And so the reason this explains Rutherford's ideas is he's saying that if particles were to go through this empty space, they could pass straight through and hit the detector on the other side. But if they were to come close to this nucleus, close to this dense region of positive charge, our electrons could be deflected. And if one came right into this nucleus, it could almost bounce straight back at the emitter. And so this explains those wide angles in which we saw things deflected. And so let's, instead of looking at our plum pudding model, let's look at Rutherford's model of the atom. Again, we'll just start out looking at several of these. So these are all representing different atoms. The little yellow part is the nucleus. And so if I shoot particles at the nucleus, we'll see that a lot of them do go straight through. Like if they go through this empty space, they can go straight through the atom. If they come close to the nucleus, we see that they kind of go off to the side. I can turn on a trace for these so that we can see some of the paths of these particles. And so again, you'll see a lot of them do go straight through. A lot of them are deflected at angles. And so this is a good model for what Rutherford was seeing. If we were looking at just one atom so you can better see, again, as they get close to that nucleus, because these alpha particles are positive and the nucleus is positive, it's going to deflect them. The ones that are closer to it are deflected more. And so that explains some of those wide angles that we see in the deflection screen. And so we have come up with new particles within our atom. And so this is huge. And again, these ones that were deflected at wide angles, Rutherford's model explains that really well, while Thomson's does not. So in the notes on this page, this just kind of summarizes some of the things I've said. And so before, we only had electrons, and electrons are negatively charged subatomic particles. We've already talked about them. They have a charge of 1 minus, and we now know that they are found outside of a nucleus in our atom. The protons are positively charged subatomic particles. They balance out our electrons, so they have a charge of 1 plus, and they are found inside of the nucleus. Now, a neutron is also within the nucleus, and it's actually neutrally charged, so it doesn't affect the overall charge of our atom. So we just say it has a charge of 0, and again, that one is found inside of the nucleus. And so how do we have different elements? Well, over time, studying them, we found that different elements contain different amounts of protons. And so electrons do not determine what an element is. What type of element is determined by how many protons they have. And how many protons they have is what we call the atomic number. Atomic numbers are found on the periodic table. I know you guys have all probably seen them. And so the atomic number is the single number towards the top. And all our elements are in order of atomic number. And so if I pull up a periodic table, this is like the one that you should have that I gave you. We see that hydrogen has an atomic number of 1. Helium has an atomic number of 2. Lithium of 3. Beryllium has 4. Boron 5, 6, 7, 8, 9, 10. And notice again that our periodic table is in order of atomic number. And so it's in order of increasing number of protons within the atom. And so hydrogen, since its atomic number is 1, it has 1 proton. Helium has 2 protons. Lithium has 3. Going down to phosphorus. Phosphorus has an atomic number of 15, which means it has 15 protons. Now, since atoms are neutrally charged, we can conclude that if we have 15 protons, and they all have a 1 plus charge, that means I have 15 plus charges. And so I must also have 15 electrons to cancel out that charge and make our atom neutral. And so the atomic number isn't just telling you how many protons you have, it also tells you how many electrons are in a neutral atom. For right now, you don't know anything about the number of neutrons. So we're going to cover that in our next little section. But this is just learning how we distinguish atoms, and eventually we're going to use this information to explain why our atoms form particular ions and they don't form other ions. And so there's just a few little homework problems to go along with this, but otherwise looking forward to continuing our discovery of chemistry here. So I hope you all have a great day. And if you need help again, we will have a daily Zoom session. So I'd really like to see you all. Hopefully I saw you all in algebra, but we'll look forward for seeing you again in chemistry. So have a great day. Bye.